Okay, in this section we're going to look at RSA encryption. It's an example of public key encryption, which was absolutely groundbreaking when it came out in the 1970s. RSA gets its name from taking the first initial of the last names of the people that published the result. And here's the thing about public key encryption. First, let's think back to the matrix encryption. We had a matrix that we used to encrypt, and in order to decrypt, we just had to find the inverse of that matrix, which, we can do if we know how to use that, Gauss-Jordan elimination. If anybody figured out what the encryption key was, if they knew the encryption matrix and that we were working MAT-2120, they could decrypt a message. So we had to make sure that when we send a message, if we want it to only be, decrypted by its intended recipient, that nobody else knows what that encryption matrix is. With public key encryption, we could tell everyone what the encryption key is and know that it is very unlikely that they're going to be able to find the decryption key just by knowing the encryption key. That's huge. In fact, that is the basis of online commerce. Public key encryption is how we send our payment information to like Amazon or whatever, and can be relatively assured. Assured enough that we do it on a regular basis, that nobody, even if they encrypted the message, wouldn't be able to decode it. They would just get some garbled, encryption, and they wouldn't know what the actual message is. So that's how public key encryption works, is that there's an encryption key that is public. So, and basically everyone has their own key. I have my own key, you have your own key. If you want to send a message to me, you do so using my encryption key. And if I want to send a message to you, I would use your encryption key. As long as I don't tell anybody what my decryption key is, then I know that I'm the only one who's going to be able to decrypt the message. And that, more importantly, you know that I'm the only one that can decrypt the message that you send to me. So basically, here's the basics for how it works. You generate your encryption and decryption keys. Then there's the encryption part that you would do to send a message to me, or that I would do to send a message to you. And then the recipient, who has the decryption key, the only one with the decryption key, can decrypt the message. We're going to go over how to generate that key and basically how to do the encryption and decryption in a moment. What we do in order to encrypt a message, we take every message and we convert it to basically a huge number. And we do this usually, in practice, it's done using the ASCII code. The ASCII code is no secret. It is just a standard way to represent the letters of the alphabet and other characters, uppercase, lowercase, punctuation, other characters, with numbers. So each of these characters, whether they're letters or special characters, will be given a value from 0 to 255. For example, M is 77, capital U is 85, a question mark is 63. And 3 digits are used for each type of character, or for each character, unless it results in starting a message with 0. So we would use 085 for you. We don't have leading, so what I mean when I say unless it results in starting M with a 0, I mean the message that we're encrypting. So we generate one big large integer that just doesn't have leading zeros. And then we use 3 digits for each character to create that. So for example, if I wanted to encrypt the message hello with a capital H and lowercase other, the letters that follow, we would write it as one large integer using the ASCII code. Here's that integer, which we're calling capital M. Capital M for like message. Now, we're going to be doing stuff by hand, just to kind of see how this process works. So to make that process simpler, we're going to use the simpler code that we used in section 5.4, right? So from 0 to 28. And in this case, the message hello, all capital letters, because we only have capital letters here, would be represented with 8, 0, 5 for E, 12, 12, 1, 2, 1, 2, and then 1, 5 for 0. We're using 2 digits for each letter, right? That's why that E is represented with a 0, 5 here, but we don't have a leading 0 in the integer itself, so that's why it doesn't begin with 0, 8, it begins with 8, because we just need to, you know, translate it into just one big long integer. So the encryption key is a pair of numbers, which we call little e and n, and we encrypt a message by computing m to raise to the e power mod n. And then the decryption key is a pair of numbers d and n. This n is the same as that n, right? So what's different is the value d, and to find our decrypted message, if I get somebody sends me this number c mod n, I take c and I raise it to the d power and reduce mod n, and that'll get me the original message. So here's how we generate the keys. RSA begins by picking two primes, which we're calling P and Q, and then you compute their product, n, which is equal to P times Q. That n is the n that's referenced here. In practice, P and Q are very large primes, maybe 100 digits or so each, and then you multiply them together. And then we compute phi of n. So part of what makes this work is that P and Q would be very large. In practice, more than 100 digits probably. So that when we tell people what n is, even though it's the product of two primes, and even though they might know it's the product of two primes, it's probably unlikely they're going to figure out what those two primes are. And then we're going to compute phi of n, and then we pick a number e. E is that part of the encryption key. We could pick any number we want for e as long as it is relatively prime to phi of n. And then we tell everybody what e and n are. That's the public part. We have to tell everybody the encryption key because they need to know how to send messages to us. Now to find the decryption key, the value of d is the inverse of e mod phi of n. So for pretty small numbers, there's a program for the TI 8384 that'll work, and I'll share that with you a little bit later. In practice, we're going to be working with bigger numbers, so we're going to the bigger numbers, that program is so inefficient. You could sit there, go make a pot of coffee, come back, you'll still be waiting for it to finish. So it is not recommended unless you're working with really small numbers. For large numbers, and I'll show you how this works, we can find it by using the extended Euclidean algorithm. So I did tell you that would come in handy, and it is going to come in handy as we work on this. And then the decryption key is the pair of numbers d and n. This you have to keep secret. I mean, you're telling everybody what n is, but I guess in particular d, you have to keep this secret. So if we make a pair of, if we make some encryption decryption keys starting with the primes 7 and 11, first of all, I'm going to tell you this is obviously not in practice, would not be used in practice. These numbers are way too small, but it'll give you the idea of like, how we do this. And then I'll show you how we can get the inverse mod phi of n. So the first thing for the encryption key, we picked the primes, and now n is p times q, which is 7 times 11, or 77. Then we find phi of n. So phi of n is phi of 77. That's phi of 7 times 11. 7 and 11, they're two primes, so they're relatively prime to each other. So that's 6 times 10, or 60. And then the next thing we do is we pick a number e that is relatively prime to 60. So I'm going to pick 53. Now I happen to pick an actual prime for e, and it's a prime that's less than 60, so I know it's going to be relatively prime, but e does not itself have to be prime. As long as it doesn't share any divisors with phi of n, you're going to be all set. So now the encryption key is the pair of values N and E, so that's 7753. I tell everyone, this is how you send me a message. Now for the decryption key. We're going to find the value of D, which is E inverse mod phi of n, or 53 inverse mod 60. And if you, you know, I'm just going to tell you what it is, and then I'll show you how we find it using the extended Euclidean algorithm. These numbers are small enough that that little program would be useful. You know, do a good job of finding that inverse, but I want to show you the technique, which I'll do on the next page. So the inverse of 53 is 17. And you can convince yourself of that. If you take 53 times 17 and reduce mod 60, you will get 1. So the decryption key, which we keep secret, is the pair values N and D, which is 77, 17. Okay, so we're on this page going to see how we find the inverse of 53 mod 60. And it starts with the Euclidean algorithm. Now, usually we use the Euclidean algorithm to see what the greatest common divisor is of two numbers. Now, we know the greatest common divisor of 53 and 60 is 1. That's why we picked 53. But we need the Euclidean algorithm in order to proceed with the extended Euclidean algorithm. So 53 goes in once with 7 left over. And then 7 goes into 53 7 times with 4 left over. Oops. And then, let's see, 4 goes into 7 once with 3 left over, and 3 goes into 4 once with 1 left over. Now, by the time I get to 1, I could include the last row if you want, but if you get down to 1, you know the last row will end in a 0, and there's our greatest common divisor. So there it is, confirmation of what we already knew, that the greatest common divisor of 53 and 60 is 1. Okay, so now we did all this so that we could use the extended Euclidean algorithm. So remember that you can always write the greatest common divisor of two numbers as a linear combination of those two numbers, and that's what the extended Euclidean algorithm allows us to do. So we're going to use this process to write 1 as a linear combination of 53 and 60. So I start with the bottom row. Rearranging it, I find that 1 is equal to 4 plus 3 times negative 1. And then I'm going to move up to this next row here, and I'm going to rewrite 3 as 7 plus 4 times negative 1. Now this is multiplied by negative 1, right? I'm bringing down this factor here. So now I'm going to kind of expand and consolidate. So what we have total, how many 4s do we have? I've got 1 right here, and then when I distribute this negative 1, that's going to become a positive 1. So I've got 2 factors of 4 plus 7 times negative 1. And you could check 4 times 2 is 8 minus 7. That is, in fact, equal to 1, so that's good. Next, I'm going to move up one line here and rewrite 4 as 53 plus 7 times negative 7. That's being multiplied by 2. And so, and when I distribute this 2, I've got 53 times 2 plus 7 times, let's see, negative 14 minus 1 is negative 15. And that is equal to 1. So I've got the 53. I want the 53. I want 53 and 60. So I'm going to now move one line up here. I'm going to use this top line to rewrite 7 as 60 plus 53 times negative 1. Times negative 15. I'm going to distribute that negative 15, so we have 53 times, okay, so when I distribute this, that'll become positive 15 plus 2 is 17 plus 60 times negative 15. So here's the result. There's 1 written as a linear combination of 53 and 60. So I'm going to explain to you why in just a moment, but once you have it written this way, this factor that's coupled with the, we wanted the inverse of 53, so that number that's coupled with it, that's the inverse. Now you have to be careful. I'm going to be really clear here. If the factor that is coupled with this number, whose inverse you want to find, if that factor is negative, the inverse is also negative, and you need to figure out what is that negative mod, in this case mod 60. Here it was positive, so we don't have to make any changes. If it's negative, you just do, if this was negative 17, we just do 60 minus 17, and that would be the inverse. But this was positive, so there's straight up what the inverse is. And here's why. So I'm going to rewrite this equation, right? So 1 is 53 times 17 plus 60 times negative 15. And that means if I rearrange this by throwing this stuff on that side, and I'm going to just write the equation in the other order. So 53 times 17 is equal to, then I have 60 times positive 15 plus 1. Positive 15 because basically I subtracted this, right, when I moved it over to the other side. And you can check and see that this is true. But this is it. When I multiply 53 times 17, I get 1 more than a multiple of 60. And that's what it means to say that 53 times 17 is equal to 1 mod 60. And that's why 17, is the inverse of 60. Of 53 mod 60. So there's our result. Here's how we can find the inverse of a number using the extended Euclidean algorithm. Okay. Let's do another one. Let's say, again, this is unrealistically small, but let's say we're going to make a pair of decryption keys starting with P is 13 and Q is 19. So for the encryption, first N is P times Q, which is 13 times 19, which is 247. Next, we're going to find phi of n. So, n is 247, but it's also 13 times 19. I'm going to just write it like that right off. And I'm getting ahead of myself a little bit, but because they are primes, they're relatively prime to each other, and I can split it up. So this is 12 times 18, or 216. Next, we pick the value of E. The only thing I need is that it is relatively prime to 216, which means it can't share any divisors. And I know that 216 is 12 times 18, so basically it can't have any 2s or 3s as factors. Those are the prime factors of 12 and 18. So let's say I don't need to pick a prime, but maybe I'll pick 11 squared, or 121. So then my encryption key, which I make public, is 247, 121. When you make your encryption key public, it is really important that you give just the value of n. You cannot say what those prime factors are. Knowing what the prime factors are makes your key insecure. So I made sure I wrote that as 247, not 13 times 19. So there's our encryption key. So now, to find the decryption key, just involves one more step, really. We're going to find the value of D which is the inverse of E mod phi of n. So that's the inverse of 121 mod 216. And these numbers are small enough I could just use that program. I want the inverse of 121 mod 216. That's 25. So the decryption key, which I have to keep secret, is the pair of numbers 247, 25. Okay, so let's see how this encryption works. So the first thing is that there is a size restriction on the message. Because we're doing our calculations mod n, the number can't be any bigger than n. And in practice, what happens is, there might be messages that are much bigger than the modulus. Even given the fact that we are using really huge numbers in practice, most messages will be still much bigger. And all they do is they chop it up into chunks that are all less than n. So you've got these different chunks coming through, and then at the end they're all decrypted, and then they're reassembled back together. If we use the encryption key from example 612, that was the first encryption key, we were working with n equals 77. Now that's pretty small. So we're basically limited to 2 digits at a time. And we can still encode a message if we split it up into blocks, right? So if I were encrypting the message hello, it would look like this, right? 1, 2, 3, 5 separate blocks. So the receiver then decrypts each block, in this case each letter, and then reassembles it. Now, this takes a little while. If I were to do hello, it would be, it would take, we have to go through a whole process for each letter. So I'm going to do a shorter version, right? Let's just encrypt the message hi, and so H is still 8, O 8, and I is 09. So we're encrypting one letter at a time. So to encrypt the letter H, remember, the way the encryption works is the encrypted message, C, is m raised to the e power mod n. So our value in that example, 612, n was 77, and n was equal to 53. E was equal to 53. So to encrypt H, I'm going to compute 8 to the 53 mod 77. And if you haven't already guessed, fast exponentiation is going to be useful to us here. So we'll just note that 53, we want to write our power as a sum of powers of 2, right? Or as a sum of powers of 2. So just note that 53 is 32 plus 16 plus 4 plus 1. And so 8 to the 53, this is going to be equal to 8 to the first times 8 to the fourth times 8 to the 16 times 8 to the 32. Those are our desired factors. We're going to make our little table. We're going to do everything mod 77. Total always starts at 1. The factor is 8 to the first, which is 8. This is a desired factor, so our new total is 1 times 8, or 8. Our next factor is 8 squared, which is 64, already reduced mod 77. This is not a desired factor, so our total holds at 8. Then we move on, squaring again, we get 8 to the fourth, which is 64 squared, and we want to reduce that mod 77. We get 15. This is a desired factor, so my new total, 8 times 15, is, and I'm reducing mod 77, 43. Okay, next. 8 to the 8th power, squaring, so I'm doubling the exponent. This is 15 squared, and I want to reduce that mod 77. 71. This is not a desired factor, so our total holds at 43. Next we have 8 to the 16, which is 71 squared. I'm going to reduce that mod 77. 36. That is a desired factor. So 43 times 36, reduce mod 77. I get 8. And then 8 to the 32nd, this is our last factor, it's our last desired factor, so it's our last factor. 36 squared. $64. That's a desired factor, so 8 times 64 mod 77 is 50. So H just gets translated or encrypted to the number 50. We don't go back to a letter like we did with the matrices. So H is encrypted as the number 50. And then we wanted to encrypt the message hi. So let's do I. So we're going to take 9 to the 53 power it's the same power, so it has the same sum when written as powers of 2. So we know what our desired factors are. 9 to the 1st, 9 to the 4th, 9 to the 16th, 9 to the 32. I'm going to make my table. My total always starts at 1. I can kind of start writing out my factors as is. I mean, I know how high I need to go. So 9 to the 1st is 9. That is a desired factor. 1 times 9 is 9. 9 squared is 81. Probably don't need the program to figure out that 81 is 4 more than 77, so this is 4 mod 77. 9 squared is not a desired factor, so our total holds at 9. 9 to the 4th is 4 squared, which is 16. Already reduced mod 77. And 9 to the 4th is a desired factor. So 16 times 9 mod 77 is 67. 9 to the 8th is 16 squared. I think I'll need the program for that. That's 25. 9 to the 8th is not a desired factor, so that's going to stay at 67. Then 9 to the 16th, that's 25 squared. That's 9. And 9 to the 16th is a desired factor, so 67 times 9 mod 77 is 64. And then 9 to the 32, that is 9 squared, which I already knew. Figured out that 9 squared is 4. So that's a desired factor. It's our last one. 64 times 4 mod 77 is 25. So that means that the letter I is encrypted as the number 25. So we would send the two blocks, 50 and 25, to the recipient. Okay, so now we're going to decrypt the message that we encrypted in the last example to see how this works. So remember that the decrypted message, which we call M, that's like the original message, is equal to the encrypted message raised to the D power mod n. So we had encrypted the message hi, and H encrypted to the number 50. So 50 got sent to the recipient. So to decrypt it, let's see, remember that our decryption key in this example, 77 is n and D was 17. So we're going to compute 50 to the 17th power mod 77. Going to make our table. Going to reduce everything mod 77 as we go. And 17, written as a sum of powers of 2, is pretty easy. 17 is just 1 plus 16. So 53 to the 17th is 53 to the 1st times 53 to the 16th power. So those are our desired factors. Our total always starts at 1. Our first factor is always our base to the first power. That is a desired factor. Oh, for some reason I wrote 53 instead of 50. I must have had the encryption key on my mind. So 50 to the first, which is 50. So our new total is 1 times 50, or 50. Our next factor is 50 squared, mod 77. Is 36. Not a desired factor, so that stays at 50. 50 to the fourth is 36 squared. That's 64. 50 to the fourth is not a desired factor. Stays at 50. 50 to the eighth, 64 squared. Is 15. Not a desired factor. Total holds at 50. And then 50 to the 16th, that is a desired. It's our last desired factor. Whoops, it's still 53. Okay, so that's our last desired factor. So 15 squared mod 77 is 71. There's our desired factor. 50 times 71 mod 77 is 8. So 50 decrypted to 8, which in our table is the letter H, which is what we encrypted to get to the number 50. I'm going to let you do the decryption for the letter I on your own time, but you should find that when you take the number 25 and you go through this process, you should find to the 17th mod 77. You should find that you get 9 when you do that. So this is the basics of RSA encryption. It's how you generate your keys. It's how you do the encryption process. It's how you do the decryption process. And I want to finish out this section, by just with a little exercise about what we need to keep private when we're publishing. This is public key encryption. But when we give the values, in our public key, it's important that we give just n, like all multiplied out. Don't give them p and q, or your encryption is insecure. So you give them n and you give them e, and that is it. And in fact, even if you gave them phi of n, they'd be able to figure out what those two primes are. So that's what we're going to end on today, is how you can find p and q if you know n and phi of n. Now, it's not just knowing n and phi of n, it's also knowing that n is the product of two distinct primes. So because we know n is the product of two distinct primes, p times q, that means phi of n is this product, p minus 1 times q minus 1. And so if you know n and phi of n, then you get a system of equations, two equations with two unknowns. So for example, if we know the value of n is 414,847, if we know that's the product of two distinct primes and they give us phi of n there, we're going to find these prime factors. So phi of n is 413,280. We know that this is p minus 1 times q minus 1. We also know that n is 414,847. So that's p times q. And if we divide by p, we get that Q is equal to 414,847 over P. Okay, so now I'm going to go back to this equation where we were right here, the P minus 1 times Q minus 1. I'm going to FOIL out P minus 1 times Q minus 1. And if you are visual and like that little table, I'll just show you, remind you how that works. So multiplying across the top, we get P times Q, and then Q times negative 1 is negative Q. On the bottom row, we have negative 1 times P is negative P, and negative 1 times negative 1 is positive 1. So this product is P times Q. Let me give myself a little bit more space here. P times Q minus P minus Q plus 1. And this is equal to 413,280. Now I'm going to do a couple of things to start off. One is that I'm going to subtract 1 from both sides. The other thing I'm going to do is substitute that in for Q. And P times Q, I know what that is, right, as a number. That's 414,847. So now what we have is 414,847 minus P minus 414,847 over P is equal to 413,279. Now I have an equation with one variable, and that is desirable for us. So I'm going to subtract. I'm going to subtract this to get all my constants on one side. So I've got negative P minus 414,847 over P. And then on this side, once I do that subtraction, I get negative 1568. And now I want this to be equal to 0. So, and well, there's a couple things I want to do here. One, we're going to end up with a quadratic equation. So there's a couple ways to go about it. One is I could have it set equal to 0, and so I could just add 1568 to both sides. It's not quadratic yet. You'll notice you might be thinking to yourself, there's no p squared, but we're getting there. Now, one of our obstacles is that we have our variable in the denominator, and that's a problem for us. So we're going to fix it by multiplying everything, both sides, by p, right? And on the left side, that factor p will distribute. So now we have 1568p minus p squared minus 414,847. I'm going to rearrange the order and also change all the signs, like multiply both sides by -1, just because I prefer to start with the leading, with a positive coefficient on the p squared. And it won't change the other side because the other side is 0. So we have positive p squared minus 1568p plus 414,847. Now, if you remember solving quadratic equations, you know there are a few techniques. One technique is to solve by factoring, but if we could solve this by factoring, we would have been able to tell what the factors of 414,847 were in the first place, and we're not really in that position, so you shouldn't be solving these by factoring. We're doing this so that we can find the factors of that number. So that leaves us with two options, either the quadratic formula or completing the square. And either is fine to use, whichever is your preferred technique. If you know me at all, you know that I am a sucker for completing the square. So that's what I'm going to do here first, and then I'll show you how we get the result by using the quadratic formula. So I'm going to go over here, and we're going to solve by completing the square. So the first thing we do when we complete the square is we throw this 414,847 on the other side of the equation, right? Subtract that number from both sides. So we have p squared minus 1568p. Gonna leave some space for the magic. And this is equal to negative 414,847. Next, I'm going to add the same thing to both sides. And what I'm going to add is the square of half that coefficient on p. So minus 1568 over 2, and then I'm squaring it. I'm adding that to both sides. So now what we have is p squared minus 1568p plus, and this is negative 784 squared. Now on the left side, because we were really clever in how we chose what number to add to both sides, this is why we call it completing the square. The left side is guaranteed to be a perfect square, so this is p minus 784 all squared. This is how, as long as I choose this number to add by taking half of this coefficient and then squaring it, this will be a perfect square. I bring down the p, I bring down this number here. That's why this is a negative, is because that was a minus 784. On the other side, I'm going to just use the calculator to do some arithmetic. So negative 414,847 plus square of negative 784. I get 199,809. And then we take the square root. We want to solve for p. P is stuck inside a set of parentheses being squared. So I'm going to take the square root. Now when we take the square root of an equation, if we're the one imposing that square root on both sides, we have to consider positive and negative roots. On the left side, you square root a perfect square, you just get rid of the square. So p minus 784 is equal to plus or minus. And in the calculator, if we have done this correctly, then when I take the square root of 199,809, it will be an integer. There's no decimal part. If I got a decimal part here, if it was like 447 point something, that means I made a mistake somewhere. So in these types of problems, it's not that quadratics can't have decimal answers, but because of the context in which we encounter this problem, we are guaranteed that when we take that square root, it'll be an integer. So this is plus or minus 447. That means that p is, if I add 784 to both sides, we get 784 plus 447, or p is 784 minus 447. So we get 1231 and 337. And these are the two primes. That we're looking for. Now, I said that you could also use the quadratic formula. So if you use the quadratic formula, you'll get the same results. This is a 1p squared in the beginning. So the quadratic formula tells us that p is equal to negative b plus or minus square root of b squared minus 4ac all over 2a, where a, b, and c come from the coefficients of the equation. So here's a, B, you have to make sure you grab the sign that goes with it. So A is 1, B is negative 1568, C is 414,847. So this would be, see, negative B, since B itself is negative, will be a positive 1568 plus or minus the square root of, I'm just plugging in the values, and that will give you the same results.